This is a fully realized interactive digital environment generated entirely from scratch based on a single text prompt. Sora functions as a data-driven physics engine, generating complex environments without using traditional rendering software. Take a look at this large industrial building on a street corner. As the simulated camera shifts perspective, the model accurately tracks how light, shadow, and geometry change across multiple angles. Maintaining that precise 3D consistency is an exceptionally difficult computational task, especially for a system trained exclusively on flat, two-dimensional video files. The architecture running this simulation contains absolutely zero explicit programming or inductive biases for 3D geometry. An inductive bias is a set of assumptions built into a machine learning algorithm to help it predict outputs for inputs it hasn't seen before. Instead, the system achieves strict object permanence simply by trying to predict the next sequence of pixels across a massive dataset. To understand how scale creates these physical rules, we have to look under the hood and deconstruct the system's underlying data pipeline. We will start with the first structural pillar, the extraction and processing of spacetime patches. From there, we examine the second pillar, the predictable scaling laws of the diffusion transformer architecture. Predicting visual data at this extreme scale mathematically forces the model to develop an internal simulation of physical reality. Early generative models were severely constrained. They typically required rigid, fixed-duration quips and only functioned within very narrow categories of visual data. Architectures like recurrent networks and early UNet diffusion models struggled to process highly variable visual inputs. A UNet is a type of neural network that downsamples an image to extract features and then upsamples it to reconstruct an output, often used for image generation. The engineers behind Sora looked to large language models, or LLMs, for a structural solution. LLMs succeed because they unify disparate types of data, text, code, and mathematics, into a single universal format known as the text token. Sora relies on a direct visual equivalent, which researchers call the space-time patch. Feeding raw video directly into a transformer network is incredibly difficult because high-dimensional pixel space requires massive, often impractical amounts of computational power to process. The first step takes raw video and shrinks it down through a compression network. This creates a representation reduced across spatial and temporal dimensions. Finally, this dense latent volume is fractured into a grid of discrete, uniformly sized cubes. By abstracting complex raw pixels into these discrete space-time patches, the model escapes traditional constraints and gains the ability to process any visual input uniformly. Historically, the standard industry technique for processing training data involved cropping or trimming all videos to a uniform square size, like 256 by 256 pixels. Engineers did this to force uniformity. Neural networks batch process data much more efficiently when every file is exactly the same shape and size. However, this preprocessing introduces a critical flaw. A rigid square crop awkwardly cuts off the subject, ruining the original framing and composition. When a model trains entirely on these cropped squares, it inherently learns to generate subjects that are only partially in view. Sora's unique patch-based architecture removes the need for uniform shapes, allowing the system to train on video data precisely at its native size and aspect ratio. We can see the direct impact on spatial composition. The exact same subject is now perfectly centered and fully visible within a widescreen frame. This method provides major benefits at inference time. The model can sample widescreen 1920 by 1080p outputs directly, without requiring external upscaling tools. Second, it can also seamlessly generate vertical 1080 by 1920 content directly tailored for mobile device form factors. This flexibility means users can rapidly prototype sequences at lower resolutions to test composition before rendering out the final high-definition video using the exact same model. Preserving the source data's native geometry teaches the model a superior level of spatial intelligence, proving that destructive preprocessing actively limits a system's capabilities. The core architectural shift inside Sora is the decision to replace the standard UNet backbone with a diffusion transformer, often referred to as a DICT. A diffusion transformer operates by taking in noisy input patches alongside text conditioning data. It then works to predict the original state of those patches, letting them emerge as clear, distinct image fragments. This design choice connects the visual model to the same powerful scaling laws previously observed in language models. The researchers found a proven mathematical correlation. As they increased the amount of training compute, there was a predictable sharpening of sample quality over time. However, scaling computational power yields diminishing returns without highly descriptive training labels to guide the model. To provide this guidance, the team integrated a recaptioning technique originally developed for DALL-E 3 to systematically generate precise, detailed text labels for the massive video training set. This creates a new problem at inference time. The average user prompt is typically very short and lacks the rigorous descriptive detail present in the model's training captions. The solution is an automated intermediary step. The system uses GPT to instantly expand brief user inputs into complex, descriptive instructions before those commands ever reach the video model. This expansion process ensures the generated video maintains high text fidelity and accurately captures the precise intent behind the user's initial prompt. The diffusion transformer architecture provides a highly scalable engine for simulating physics, while the GPT-enhanced language grounding acts as the vital steering mechanism. With the architecture mapped out, we can reevaluate the initial claim that this system functions as a world simulator. There are clear examples of successful emergent interaction. The model can simulate a painter weaving new strokes on a canvas that persist correctly over time. It also demonstrates success in maintaining long-range coherence, successfully rendering a single character with identical features across multiple distinct camera angles within a single generated sample. But we must look closely at the errors. The current iteration remains a deeply flawed simulator when it encounters strict physical laws. This is a video of a glass cup shattering. The model entirely fails to simulate the correct rigid body dynamics of the impact, resulting in an unnatural fluid distortion rather than a physical break. It also struggles with complex state changes. There are multiple instances where subjects consume food on screen without actually leaving bite marks on the object. Furthermore, in long-duration samples, the model frequently hallucinates spontaneous object appearances, generating items that emerge inexplicably into the frame. These specific incoherencies prove that the model is still approximating physics through deep pattern recognition. It is not calculating true mathematical physics. However, the core finding of the technical report stands. Despite these persistent failures, the trajectory of improvement through data scale is clearly documented. Scaling patch-based diffusion transformers has proven to be the definitive blueprint for building a general-purpose simulator capable of rendering both physical and digital realities.